Hello everybody and welcome to today's video on chapter 3 of Calculus and Vectors. Today we'll be going over chapter 3.4, which focuses on simple rational functions. That might sound familiar to you because we've actually covered this topic in advanced functions for a whole entire unit, but now we're gonna skim over it in one chapter, and the reason for that will become extremely apparent to you in a couple of moments. So today we're gonna focus on two primary things. We're gonna talk about how the derivatives of rational functions can be used to help us sketch a graph of a rational function, and then we're gonna talk about the concavity of rational functions, how we could find it, and how again it could be used to graph those functions. So let's get started on that. The derivatives of rational functions come about in chapter 2, I believe, when we're dealing with stuff like the chain rule and the quotient rule. And the reason why it comes up is because we're going to be dealing with something that has a fraction, right? We have a variable in our denominator. That is what creates a rational function. So when we want to graph a rational function in grade 12 advanced functions, we would find out how to factor it, right? We knew the three different ways that rational functions could be presented. And once we factored it, we would create an interval chart, discover where it goes up and down, so increasing and decreasing, and from that we would make a graph. However, we were very limited to our factoring techniques back then. And it was also very difficult for us to deal with certain types of rational functions because they were not factorable. But now that we know derivatives and also limits, we can actually overcome those obstacles in calculus. So today we're going to take a look at how we would do that. So for example, let's consider this function here. This is a very simple function that we would have seen in advanced functions. So we should have no problems in graphing it in the old way. However, since we're trying to learn new concepts, we should also learn how to graph it in our new way. So the first step would be like we did in in advanced functions, it would be to find its asymptotes. So we could either have a horizontal asymptote with a vertical asymptote, or an oblique asymptote with a vertical asymptote, right? So in our case, we have a constant at the numerator, which would mean we can't have an oblique asymptote, and we have a vertical asymptote here since we could create a value for x such that the denominator is equals to 0. So in our case, you have x squared minus 9, so x squared is equals to 9, so x is equals to plus minus 3. Again, the way I got that was just taking the square root of 9. Now that we know what x is equals to, we know the equation for the vertical asymptotes. We also know the equation for the horizontal asymptote, which should be y is equals to 0, since again this was a constant, and this is just x squared. So now that we know that there's these asymptotes in our advanced function style, we would use those asymptotes to find the intervals where it's increasing, where it's decreasing. However, now we need to understand why that asymptote is there and how sometimes this can't be an asymptote. So we need to actually prove it by finding the one-sided limit. Again, you don't have to do this all the time since, for example, here we know the vertical asymptotes will be present at -3 and +3, but in some cases it might be less obvious than you think, and so this cheeky little test will help you realize whether it's a vertical asymptote or not. The test itself is very, very simple. You need to just find the left side limit and the right side limit of that point. So if we were to look at x is equals to -3 and take the limit of f of x as x is approaching -3, we would see that we are getting more and more positive as we approach it from the left-hand side. However, if we were approaching it from the right-hand side, we would see that it's getting more and more negative. Since we know that a limit can only exist when the right-hand side equals to the left-hand side limit, that doesn't occur here, so there's no limit, therefore there is a vertical asymptote. You could do this exact same test for when x is approaching positive 3 and you will get the same results. So now that we know our vertical asymptotes, we need to actually determine the intervals of increase and decrease. So luckily for us, we learned how to do that in chapter 3.2, right? That was our first derivative. So given f of x, we can easily find the first derivative of it. So here we just rewrite x squared minus 9 in the denominator as just x squared minus 9 to the power of negative 1. And now we could apply our power rule and then so the chain rule here in this case, and we would figure out that we actually have f prime of x is equals to negative 1 times x squared minus 9 to the power of negative 2 times 2x. If you don't remember how this happened or what the chain rule is, I recommend checking out my video on the chain rule, which I will link in the description below. But now that we got to this step, all we have to do is rewrite it back into a rational form. And so we get f prime of x is equals to negative 2x divided by x squared minus 9 squared. If you remember what a critical point is, the critical point is where f prime of x is equals to 0. So when the numerator is equals to 0. Here we have negative 2x. Since we have only one variable, x must be 0. So now that we know our vertical asymptotes and our critical point, we can construct an interval chart. From our interval chart, we can actually figure out very easily whether the function is increasing or decreasing. So here, I put all of our intervals down, then I choose a number between negative infinity and negative 3. For example, negative 4. You plug that into your calculator. If it spits out a positive number at you, just put a plus. You could put the whole number down, but that's extra effort, so I don't recommend doing it unless your teacher forces you to. We also are going to specify where our vertical asymptotes were and where our zeros were, so that we know whether or not those points can exist and should be put on our graph. So when we do this whole procedure, we figure out that our function is increasing when x is less than 3, and it's also increasing when x is in between negative 3 and 0. We know there is a point at the origin when x is equals to 0. Then after that, between 0 and 3, the function is decreasing, and then again it will be decreasing as x becomes greater than 3. So now we could clearly see why those vertical asymptotes are very important. If those were points, then we wouldn't get this shape over here, right? This is what happens when we actually graph it. If it was a point, then we would just have a positive slope like that and a negative slope. But since we do have the vertical asymptotes, in order for these to be increasing here and decreasing here, we actually had to specify where they were. So if you don't remember why this right here is increasing and so is this, and why this is decreasing and so is this, I'll explain it to you right now. So if we look at this branch, we know that it should be increasing, and it's really easy to see. As we approach it from this side, we see that we are getting more and more positive. We're getting bigger and bigger numbers. So that would mean that we are indeed increasing. Again, if we start here and we go from negative 3 to 0, we see that we're going from very negative numbers to numbers that are approaching 0. So again, we are increasing. Now, if we go from this side and we look at what happens, we see that we're going from numbers that are around 0 to very negative numbers. So we are actually decreasing. And similarly here, if we go look from these numbers right here, which are very, very positive, then they start going down to around 0. So again, we're decreasing. This might be a little bit confusing since last year we learned about decreasing positives and increasing negative slopes and stuff like that in rational functions, but now you should just keep this in mind rather than what you learned before so you don't get confused. So just try not to remember what you've learned in advanced functions for now, because if you don't understand it fully, you will get yourself confused. So just simply right now, when it's saying increasing, that means the numbers are going up, and when it's decreasing, that means the numbers are going down. Finding the limit is a little bit more tricky because we need to actually now look at what happens as we approach that vertical asymptote. As you said here, we were approaching it from the left, and when we got closer to it, we got to very positive numbers, so very large positive numbers, which would mean we're approaching positive infinity. However, when we were going away from the asymptote, right, so still increasing, that would mean that our original limit at around -3 was actually negative infinity, since we were starting at very large negative values. Similarly, on this side, when we were looking here, right, we were going to very negative numbers, which would mean we're approaching negative infinity. However, on this branch, we were starting at a very large positive number and then going down, which would mean that the limit at -3 from the left-hand side, or sorry, the limit at 3 from the left-hand side is negative infinity, and the limit at 3 from the right-hand side is actually positive infinity. So again, you could sketch it out and figure out when it's approaching positive infinity and negative infinity, which I wouldn't recommend since you need to actually know why that happens. But if in case you don't know why that happens, you could do this little test where you take a very close number to your asymptote, and then you would figure out if it's very positive or very negative, and that would tell you whether or not it's approaching positive infinity or negative infinity. So now let's move on to concavity of rational functions. So as we learned in chapter 3.3, the second derivative test lets us find out the concavity of functions. Rational functions are no different, so we could use the second derivative test to find the concavity of them as well. So here I have a pretty difficult example so that we actually know exactly what's going on when we're dealing with simpler examples. And that function that we're going to deal with is this here. So we have 64x squared minus 4 all divided by x cubed. So if we want to find its concavity, we would have to find its second derivative. To find its second derivative, we must find its first derivative first. So right here, we know that when we have something in the denominator, that just means that something had an original power of a negative number. So if this was 3, that would mean its actual power should have been -3, which is what I've written down here. Now, from here, we can actually use our derivative rules. So this is actually the product rule that we learned about in chapter 2.2, I believe. So if you don't remember that, again, go check out the video. But if you do, you could see that we found the derivative of this side first, right, and then multiplied it by the original value of the second part. Then we kept the first part, and we found the derivative of the second. Then we added the two together. Now it just becomes basic algebra. I opened these brackets and got 128x to the power of -2. And then when you open these brackets, you actually get -192x to the power of -2 plus 12x to the power of -4. Collecting like terms gets you this value right here. You could try and go further by factoring it, but remember we need to find the second derivative, so I decided to stick with these values for now since they're still pretty easy to work with. So here we actually had the sum of two functions, right? Which would mean we just need to find the derivative of the first part and the derivative of the second and add them together. So the derivative of this is this here, and the derivative of this is this here. Multiplying all of the terms, we get 128x to the power of -3 minus 48x to the power of -5. Now we could actually make it look nice and pretty since we're done with our derivatives. So to do that, we would actually factor out x to the power of -5. If you factor out x to the power of -5 from x to the power of -3, it's the same as subtracting -5 from -3, which is equals to 2. So that's why we get x squared here. Then over here, we just took out the x to the power of -5. Again, if we have a negative power, that means it should be in the denominator, and so we get our final-ish answer of 128x squared minus 48 divided by x to the power of 5. The reason why I say ish is because we could continue factoring it further, since we have two positive even numbers, or sorry, we have two even numbers in our numerator, so we could definitely at least factor out a 2. But since we need to find the roots, it's not necessary right now, since we'll be doing it in 2 steps from now. So again, when we want to find the points of inflection, or even the intervals that we're working with, we would need to find our that when f double prime of x is equals to 0. So here, this is a simple quadratic equation. We move the 48 to the other side, divide by 128, and take the square root of it. And so that's what we get here. 48 divided by 128 actually simplifies to 3/8. We know that f double prime of x does not exist when x is equals to 0, since if it were to equal to 0, then our original function would have 0 in its denominator, and that can't happen. So using that, we could actually create this interval chart here. We would go from our key points. So that was this negative square root of 3/8, 0, and positive square root of 3/8. Plug in values between these intervals into your calculator, and you would get negative, 0, positive, does not exist, negative, 0, and again, a positive. So now, if you remember what these mean, whenever we have a negative, that means it's concave down, and whenever it's positive, that means it's concave up. So when we look at it, the full picture, we actually figure out that we were going concave down until we hit our point of inflection at negative square root of 3/8 and negative 87.1 around there. Then we started going concave up until we hit our vertical asymptote. After a vertical asymptote, we started going down, so concave down like a frowny face. We reached our point of inflection once again, and then we started going back up. So if we wanted to actually see the graph of this, it would look something like this. So this is the graph of our original function. The reason why I didn't actually go through the whole question of developing what this graph looks like is because we're going to cover that in chapter 3.5, which is combining all of the different steps we learned to create any type of function using the given information about it. However, if we look at the info that we found, which was that it was concave down at certain points where its inflection points were, we can actually verify whether or not we created the right interval chart and got the right information. So at first, it says it was concave down, and then we reached our POI at the square root of 3/8, and then we went concave up. So over here, it definitely does look like a frowny face, right? Then we're supposed to reach that point over there, and it's supposed to look like a smiley face. As you can see, it definitely does look happy now. The only problem is that this point right here doesn't seem like a point of inflection, since it's not like a clear cut between when it's going down and between when it's going up, which is actually why it's so wonderful for us to have discovered where that point was, since it's really not clear on the graph itself. But if we continue looking at what happens on our graph, we could see that it's going up, which is concave up, all the way to positive infinity, right? Because here, as we said, at 0, we should have a vertical asymptote. As you can see, we keep approaching those values, but we never get to 0. So that means we found that out correctly. Then we said that we should be going concave down until our point of square root of 3/8, 87, and then we will go concave up. So if we look at our graph again, we're going up but it does seem like over here especially we've been looking at a frowny face, so it was indeed concave down. Then after our point of inflection, we're actually starting to look like a smiley face, so we were indeed going concave up at that point. So as you could see, finding the second derivative of that function was actually super beneficial, since now we could have easily put these 4 curves correctly on our graph. The only thing that we wouldn't know would be our zeros, which are right here, which we could find using the first derivative, and then we could kind of be a little bit fuzzy about where the horizontal asymptote is, but we will also go over that in the next chapter. So now we are done with chapter 3.4. As you can see, it's a little bit on the heavier side in terms of the concepts that you need to know from previous chapters. However, I would say chapter 3.5 is probably the most complex, just because you need to put everything you know together for that part. But either way, if you want some extra practice, I recommend doing 1 and 2. 1 and 2 are directly related to one another, so just do parts B, C, F, and G for it. Then just do 4, and question 9 is more of a thinking part because it actually has a x over x plus 1 as its function, and then you have to go through all the steps that we did today. So hopefully you've enjoyed today's video. I've had a lot of fun making it. Again, thank you so much for watching, and I hope to see you guys next time. Bye bye!